Hi, I'm Navid Salehnamadi, a member of Software Engineering and Analysis Lab in University of California, Irvine. I'm going to present our paper in ASE2020, AR Catcher, a static analysis framework for accurate and scalable event race detection in Android. Concurrency are intertwined with mobile apps as they interact with various entities such as users through graphical user interface, device resources such as battery, external resources such as web, and many other things. To support all these external and internal interactions efficiently, Android provides an event-driven concurrency mechanism and various libraries. However, concurrency is a major source of confusion for developers and is among the top 5 reasons for bugs in Android apps. One of the common types of concurrency bugs is event races. An event race is accessing a memory location by two events without any specific order, where one of the accesses should be right. For example, let's say there are two events that access a memory location, field X, and one of the accesses is right. Since there is no specific order between these two events, there are two possible scenarios. When the left scenario is executed, no problem occurs. However, when the second scenario happens, a null pointer exception will be thrown, which is an example of different behaviors in different scenarios. Detecting event races have been heavily studied in the literature. However, the conventional techniques cannot detect non-multithread issues in Android, since they do not consider the event-driven model. Also, they do not support concurrency libraries that developers commonly use. Android-specific event race detection can leverage dynamic analysis techniques, which are quite precise, but may miss true event races since they do not cover the whole application and just analyzes the execution traces. Another group is static race detections that analyzes the whole source code, therefore minimizes the risk of missing an event race. However, the existing techniques have their own limitations, including imprecisely modeling concurrency in Android that can lead to missing event races. Moreover, these approaches are not scalable. For example, one technique takes 50 minutes on average to analyze an app. Additionally, their models are defined over a fixed set of concurrency libraries. Another issue with the existing technique is that their corresponding tools are either unavailable or closed source, making it difficult to continue this line of research. To mitigate the aforementioned limitation, we introduced AR Catcher, a static analysis framework for effective detection of event race defects in Android apps. In AR Catcher, we introduced three novel concepts: Concurrency-aware summary functions, CSF in short, context and concurrency-aware call graph, C3G, and a static vector clock, which is inspired by the concept of vector clock in distributed systems. For the rest of the presentation, I show you an example to be familiar with event races in Android. Then I describe our approach and show how AR Catcher is accurate and fast. Next, I present our extensive empirical evaluation, and finally, I conclude this presentation. The example is a simple time tracker app. When the user starts the app, it initializes this screen and its internal variable by communicating with an external server to store time. When a user presses the record button, the app calculates the difference between the current time and the last time stored in the server. Now let's take a look at the code. On the right hand, you can see the timeline of the executed events sorted in their corresponding threads. The left side is onCreate method, the first executed method in the app. It first shows the content on the screen, then sends an event to initialize the internal variables on UI thread. Note that UI thread has a queue of events that execute them sequentially. Finally, it executes an async task to store the current time on the server. The method execute_on_executor runs synchronously during onCreate events and calls doingBackground method asynchronously on serial executed thread. The current time, let's say 10, passes to doingBackground as the last parameter. Then the onCreate event is done. The initTime event initializes some internal variables, such as start time, and updates the screen and finishes its work. doingBackground event sends the received current time to an external server. Note that the network communication may take an uncertain amount of time. As a result, the complete time of doingBackground is undeterministic. Once the doingBackground event is done, the current time will passes to an onPostExecute method, which is executed in UI thread. onPostExecute updates the value of start time, since it's a negative value, and updates the screen. When the user clicks on the record time button, onClick method is executed and invokes the same async task that onCreate invoked before. Note that in this method, the async task will be executed in thread-pool thread. Similarly, the doing background event of onClick, known as dib-1, communicates with the server and passes the result to onPostExecute. OnPostExecute computes the elapsed time using previously a start time and updates the screen. However, there is another possible scenario. Let's say the doing background event takes longer than expected. If the user clicks on the record time button during the execution of doing background and onClick's doing background event finishes sooner. Once the first doing background is finished, the elapsed time becomes negative value, which is incorrect. This issue is an example of an event race bug in this application. Recall that an event race is accessing a memory location by two events without any specific order, where one of the accesses should be write. In this case, onPostExecute method has both write and read access to a start time field. Since there is no specific order between execution of onPost events, both two scenarios are possible. As can be seen, detecting such issues are difficult, especially for static techniques that do not have any information in runtime. Particularly, there are several factors that need to be considered for precise static analysis. First, it should be flow sensitive. Otherwise, it may mistakenly consider initTime and onPostExecute as an event race. However, since the invocation of initTime happens before the invocation of onPostExecute in UI thread, the scenario that onPost happens before initTime is not possible. Moreover, the analysis should be thread sensitive. Otherwise, it cannot distinguish between events executing in different threads, resulting to miss a true event race by assuming all events are executing in one thread. It also can report the false event race by assuming each event is executed in different thread, even though they executed in the same thread. Finally, the analysis should be context sensitive, since event races can be caused between different executions of one method, such as onPostExecute. Although there is only one method, two different events are created caused by different contexts, onCreate and onClick. Now we go through our approach and provide a brief overview of how ErCatcher detects event races statically. Given an app or APK, ErCatcher uses Spark to generate the points to set for analysis on the memory location of object fields. Then, given the app and its points to sets, ErCatcher detects all event race candidates without considering their order of execution. Next, using FlowDroid, ErCatcher generates the app's call graph CG. This is a subset of the call graph of our example generated by FlowDroid. Now we explain Concurrency-aware summary function to show how, given CG and manually generated CSFs, ErCatcher augments the CG and generates Concurrency-aware call graph. We decompose an event into three execution states: its invocation state, when the event is dispatched, and its start and end states, corresponding to the start and end of the event body. These states help us to represent the notion of time with abstract graph nodes. We introduce Concurrency-aware summary function, in short CSF, to avoid redundant computations. CSFs are generated for each method automatically using a static intra-procedural analysis, which can be done quickly. CSF is a directed cyclic graph where the nodes capture the information related to concurrency behavior of the method and the edges capture the control flow. For example, the CSF of onCreate method is this graph where it starts with an start execution state, followed by two asynchronous invocation states, and finally the end state. For methods in concurrency libraries, we use manually implemented CSF to increase the accuracy. Using library CSF helps us to overcome the inaccuracy caused by the over-approximation in static analysis. Moreover, using library CSF, developers can even model their own custom concurrency libraries, making our approach extensible. By combining the generated CSFs and call graph, we come up with Concurrency-aware call graph C2G, which is flow sensitive. This graph shows subset of C2G of the example. Then, using a list of event traces candidates, ErCatcher augments the contextual information to C2G and generates context and concurrency-aware call graphs. C3G increases the accuracy of our analysis by augmenting the concurrency and contextual information in interprocedural level into a regular call graph. For example, this figure shows C3G of the example app. There are two nodes corresponding to onPostExecute methods initiated by onCreate and onClick. Moreover, the running threads of doing background methods are determined, making C3G context and thread sensitive. Furthermore, to reduce the computation time, C3G only keeps information relevant to event races. For example, it does not contain anything about setContentView method since it is not involved in any candidate event races. Next, in HappenBefore analysis component, the SVC of each node in C3G are computed. Vector clock is a well-known concept in distributed systems to determine partial order or happen-before relation between events. Each event is associated with a vector of logical clocks, and increment the logical clock corresponding to its thread. If an event is caused by another event in different thread, it updates the corresponding clock to the maximum value. Therefore, logical clock represents the latest timestamp prior to an event. Given vector clocks, we can determine happens-before relation. For example, event 1 happens before event 4 because all of its clocks are smaller than event 4 clocks. However, there is no happens-before relation between events 1 and 2 since there is no deterministic order between their vector clocks. Inspired by vector clocks, we introduce a static vector clock in Android. Each node is associated with a static vector clock that shows the latest event's execution states prior to this node. Using a static vector clock, we can determine the end of init time happens before the start of onPost 0. And also there is no happen-before relation between two onPostExecute events. Note that an event happens before another event if its end state happens before the start state of the other event. Given C3G, SVC, and the list of event race candidates, the thread-sensitive filter component filters out false event races. Finally, ERCatcher prioritizes the event races and gives high priority to event races with more confidence, and reports the results. We evaluated ERCatcher to answer the following 4 questions. In this presentation, we explained the first 2 research questions in detail. We conducted our experiments over 3 different datasets. First, Benchroid, which is a micro-benchmark of event races in 34 Android applications. Second, a curated dataset of confirmed event races in 31 real-world apps reported by prior studies. And finally, a set of 500 randomly selected apps from F-Droid App Store. To compare ERCatcher with the existing work, we use Nadroid, the state-of-the-art static event race detection in Android. Nadroid is designed to report use after free bugs, which is a subset of event races. Although ERCatcher is able to detect general types of event races, in these experiments we only compare the reported use after free event races. Nadroid uses 2 sets of filters, sound and unsound filters. The unsound filters reports a smaller number of warnings. However, it may miss some true event races. In the first research question, we want to measure the accuracy of ERCatcher in detecting true event races. The table on the left summarizes the result of applying Nadroid and ERCatcher on Benchroid dataset. The highlighted columns show the result of Nadroid sound and unsound respectively. And the last 2 column shows the result of ERCatcher. The first one is the all event races and the second one is the high priority event races. We categorize the subject apps into few categories that represent the type of bugs. As can be seen, the flow sensitivity helps ERCatcher to report less false positives, and the thread sensitivity helps it to not miss through event races. Overall, ERCatcher could outperform both versions of Nadroid in terms of precision and recall, and it has 11% improvement in F1 measure. Besides that, we evaluated both approaches on the curated datasets, and ERCatcher detects all confirmed cases. Nadroid could detect 88% of them. We could not report precision for this dataset since it does not contain the false positives. Next, we answer how scalable ERCatcher is. The following tables shows the computation time for Nadroid and ERCatcher to detect event races. As can be seen, ERCatcher finishes the analysis between 12 and 13 times faster than Nadroid. Moreover, we run both tools on 500 randomly selected real-world apps with 5 minutes time limits. Nadroid only finishes 30 applications or 6% of all apps on time, while ERCatcher analyzed 459 apps or 91.8% under 5 minutes. Moreover, Nadroid crashed during analysis of 316 apps, meaning it cannot analyze 63% of apps irrespective of time. This shows ERCatcher is capable to be used in practice. In conclusion, we presented ERCatcher, an accurate and scalable event race detector in Android. We introduced 3 novel concepts for analyzing concurrency in event-driven systems. We evaluated our approach using real-world apps, and compared to the state-of-the-art, ERCatcher is substantially faster and more accurate. We released the source code of ERCatcher and all apps under experiments. Thank you.